Hello students, welcome to part 8 of the chapter Chemical Kinetics. In this part we are going to see about unit of rate constant. So in the last part we have seen as a part of rate law, there is a proportionality constant, rate constant denoted by the letter K. So in this part we are going to see the unit of rate constants for different order of reactions. Unit of rate constant K. So for a reaction where there is only one reactant R, according to rate law, rate is equal to K into R raised to X, where X is the order of the reaction. So if you rearrange this, what is K? K is equal to rate divided by concentration of R raised to X. You just rearrange the rate law. So what is the unit for a rate which we have seen in previous part? Rate is nothing but mole liter raised to minus 1, second raised to minus 1. On the other hand, we have molar concentration here, it is mole per liter. And on the power, on the x as an exponent, you will get the order of that particular reactant. So if the overall order of the reaction is zero order, so the entire unit of rate constant K will be like this, where X will have zero number. So you will get something like this: mole liter raised to minus 1, second raised to minus 1 divided by mole per liter raised to, the exponent is 0 because it's a zero order reaction. So what will be the unit of K then? The entire denominator becomes unity. So the unit of K will be the unit of rate itself, that is mole liter raised to minus 1, second raised to minus 1. And if you look into the order of the first order reaction, so you will have the same equation, but here the value of X will be equal to 1 in this case. So let's see, mole liter raised to minus 1, second raised to minus 1 divided by mole per liter whole raised to 1. That means the denominator stands. And this mole and this mole will move out, this one and this one will move out. Finally we will have only second raised to minus 1. So the unit in the case of first order reaction is second raised to minus 1. Whereas the second order reaction, for second order reaction we will have the same equation, same units, provided that the X value of X here will be equal to 2. So if you substitute, you will get like mole liter raised to minus 1, second raised to minus 1, mole raised to 2, liter raised to minus 2. So mole raised to 2, 1 mole out of it will cancel out with this, and liter raised to minus 2, 1 L minus 1 will cancel with this one. So that means that we will have some unit like this mole, when the remaining 1 mole, that is if it is going up to the numerator, you will get mole raised to minus 1, liter raised to minus 1 that was remaining here will go to the numerator, and you will get liter raised to 1 and second raised to minus 1. So to make it into a table, you will get it like this. It is the reaction order, and for each reaction order, in the case of 0, 1, 2, K value depends upon the rate and also the order. So finally you will get units like this. These units you have to by heart. Mole liter raised to minus 1, second raised to minus 1 for 0 order, and for the first order it's second raised to minus 1, and for the second order it is mole raised to minus 1, liter raised to 1 and second raised to minus 1. For the board exams, they usually ask to identify the order based on the unit. One such question is like this: identify a reaction order from each of the following rate constants. So they will provide the value of rate constants along with its unit. You can see it, one unit here is here and one unit is here. And from the slide that we just saw, we know that for first order, second order and zero order we have specific units. And we have seen such a unit where mole raised to minus 1, liter raised to 1, second raised to minus 1 was 4, liter raised to 1, mole raised to minus 1, second raised to minus 1 was for second order reaction. And in this case it is second raised to minus 1, and this was for first order reaction. So if you know the units of each order, then it will be easier to identify the order of that overall order of that reaction. Now next another question. The decomposition of ammonia on platinum surface is a zero order reaction. So this example, the reaction given in this question is very important because this we will learn again as example of zero order reaction. Decomposition of ammonia on a platinum surface. One more addition, that is on a platinum surface of high temperature and high pressure. So if you add that, it will be perfect. The decomposition of ammonia on platinum surface is a zero order reaction. What are the rates of production of N2 and H2? So upon decomposition, ammonia will give out nitrogen and hydrogen. So we should write that equation to know the stoichiometry. And the value of K is given. If K is given, definitely we can go for a rate low. And according to the rate law, order of the reaction is zero order. So let's see how to solve this. First we have to write out the decomposition reaction, that is ammonia will give nitrogen and hydrogen. And if you balance it, you can see that clearly it's the reverse reaction of Haber's process. And this reaction is not reversible in this case. When we are using platinum as the electrode, the entire ammonia formed will go and produce nitrogen and hydrogen. So as we have already learned how to write the rate, how to equate the rate with respect to reactants and products. So rate is equal to, you can write it like this. When it comes to reactants, you have to add the minus sign. Rate of decomposition of ammonia divided by the time interval, the whole by its stoichiometry. So ammonia has a stoichiometry of 2. You divide the rate divided by 2. Then if you equate it with products, you will get like change in the concentration of, or increase in the concentration of nitrogen divided by the time, and its stoichiometry is 1. And in the case of hydrogen, again increase in the concentration of hydrogen divided by the time interval, the same time interval here, all divided by its stoichiometry, that is 3. So you will get the rate. This is actually to confirm or to find out the rate of production of N2 and H2. Okay, according to rate law, we know that rate is equal to K into concentration of the reactants raised to its order. So already they have mentioned that it's zero order reaction. So you can say that it's K into molar concentration of ammonia raised to 0. And it is given, K is given, that is 2.5 into 10 to 6. So that means that, which means that the rate is equal to rate constant. So that is rate is equal to 2.5 into 10 to minus 4, since it is an zero order reaction. Now if this is the rate, you can say that clearly, you can see it, that rate is the rate of production of nitrogen, because you don't have to divide it with any stoichiometry. So rate of production of nitrogen is the same as the rate of the reaction, 2.5 into 10 raised to minus 4. So this statement means it is the rate of production of nitrogen. On the other hand, the original rate of production of hydrogen is only the 1/3. The original rate is only 1/3 of the real production of hydrogen, because we are dividing the real rate of production of hydrogen by 3. So that means that this rate what we got here is only 1/3 of the real rate of hydrogen, rate of production of hydrogen. So what you have to do, you have to multiply it to get the real rate, or the overall hydrogen production. Rate of production of hydrogen is equal to 3 into 2.5 into 10 raised to minus 4. Again I will repeat. So the rate what you are going to get here, what we got here, is only 1/3 of the real production of hydrogen here. That's because according to the equation, what is rate? Rate is 1/3 of the hydrogen production. So if you want to get the real want to get the real concentration of hydrogen produced, you have to multiply the rate with 3. So that's why we have multiplied here with 3 in order to get the real rate of production of hydrogen, and it is 7.5 into 10 raised to minus 4 mole liter raised to minus 1 second raised to minus 1. So I hope you have understood this session. Thank you.